Hey, this is Joel Duff. Welcome back. Really quick story today. I have a picture here in front of you of the Bighorn Basin, specifically Sheep Mountain in the Bighorn Basin. A few years ago on family vacation, we spent almost a week in this particular area of Wyoming. The principal reason for being there was to do some fossil hunting and to explore this particular landscape. And we hiked this particular mountain one day, or I did with my two sons. And I was reminded of that today when I saw a Facebook friend of mine posted an article about a potential large meteorite impact that struck Wyoming about 280 million years ago, and some of the evidence for that. And that had me scratching my head. I was like, I remember seeing something there when we were hiking up the side of this mountain that I was very curious about. And this made me even more curious. I'm going to show you a couple. So I drudged up a couple pictures of our hike. And fortunately, I did take a couple pictures of the object that I saw that I sat and wondered about for a few minutes. And they're not especially exciting when I show them to you. But what I'm going to do is I'm going to show you the paper, talk a little bit about, just briefly, about this evidence that a large meteorite might have struck or the Wyoming-Nebraska border, and how they've inferred that from evidence from a number of different locations in Wyoming. And that's also going to give me an excuse to show some other vacation shots and talk a little bit about this particular area. All right, so photos of Wyoming, talking a little bit about meteorite impacts in the past. And I'm even going to tie that into a challenge to, say, young Earth creationists to explain what I think is a very difficult problem, which is explaining the evidence of meteorite impacts in sedimentary layers, presumably set down in a global flood all at one time. We've got all that coming up. All right, before we get to some vacation shots from my trip to Wyoming, let's take a look at this paper from the Geological Society of America. Actually, this is the bulletin from the Geological Society of America, and it is this report from, actually it's late 2022. Secondary cratering on Earth, the Wyoming Impact Crater Field. Right, so now this question of secondary crater, what is a secondary crater? A secondary crater is when a large object strikes the Earth, throws up material into the air, and that material has to land somewhere, right? And if it's large enough objects, they're going to make secondary craters. And so that is what's been found in Wyoming and a number of different locations are presumed secondary craters. These are craters that at one time were suggested to be actually meteorite craters. But upon further investigation, they discovered there's no meteorite remains and other types of evidence you'd find from a meteorite impact in the bowls of these craters. However, these particular locations have evidence of a large impact of some type. Now, there's very few other possible explanations for these structures, which I'll show you a couple pictures of in a moment. Anyway, we got this paper by Kankman et al. Again, like I said, in the bulletin of the Geological Society of America. So let me just briefly read the abstract. A number of small impact structures have been discovered in Wyoming, and we raised the question of how this accumulation occurred. We documented 31 crater structures, 10 to 70 meters diameter with corresponding shock features, but missing meteorite relics. So here you have craters with some form of shock features, but they're missing meteorite relics. So what are they? Where do they come from? All craters occur among the outcrops of the uppermost Permian-Pennsylvanian Casper Sandstone Formation, which are about 280 million years old. So I'm going to show you a map of the area in Wyoming that we're talking about. And these craters are in different locations, but they're all found in the same layer of rock dated to the same age. So that's a really fascinating thing in itself. And it's suggested to them, initially, individual craters would have been investigated. But as you investigate more craters and realize they're all coming from the same formation in the same exact time period, kind of little light bulbs got to go off in your head. And you got to think, maybe all these craters are related to one another. If they're related to each other, maybe they're a meteorite comes streaming in from an extraterrestrial meteorite, right? Comes streaming through the atmosphere, breaks up into smaller pieces, falls on Earth, and creates a whole bunch of meteorite impacts. right? Great hypothesis. Go test that hypothesis. Well, we should find evidence of actual remnants of meteorites inside of these meteorite craters, and that evidence is lacking. And yet there is a crater-like bowl that is found embedded, that's preserved for us in rock. On a bunch of these different bowls, as I said here, 31 crater structures have these features. And as we're going to see, there's actually a lot more, but they just haven't studied them yet, but they're all in the same layer of rock. So probably there's going to be a whole bunch of additional evidence once those are further investigated. Their spatial arrangement shows clusters and ray-like alignments. So boom, 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 whole series of craters sort of one after each other, almost like a large amount of material spewed out, right? A huge rock that breaks into several pieces and then kind of falls farther away in several different large impacts. The radial arrangement of trajectories indicates that the craters are secondary craters formed by ejecta from a primary crater whose likely position and size are reconstructed. Modeling ballistic trajectories and secondary crater formation indicates that impacts occurred around 700 to 1,000 meters per second and caused small shock volumes with respect to crater volumes. This is the first field of secondary craters found on Earth, and we disentangle its formation conditions. So that's what they're going to do in this particular paper. And we're not really going to look at much of it. I'm simply going to scroll down here to the primary figure. And here we have a section of the southeastern portion of Wyoming. Here's Cheyenne down here in the bottom. So what you're seeing in this figure is the blue, the blue outline material, which is the rock at the surface, which is colored blue. That is all Carboniferous rock. So this is this rock that's 200 million 80 years ago. In fact, the rock that has that's blue and then has red next to it is the boundary between the Carboniferous and the Permian age. And then the black dots, right, or the black circles, the white interiors, those are the 31 different craters that they have studied and identified as all being from the same point in time and having similar characteristics. And so they think that all these craters are related to a single event. And you can see they cover quite a span of area. So they're many dozens, if not more than dozens of miles away from each other. Lots of them are clustered together, but of course they're only found, and note, they're only found in these blue rocks, right? These Carboniferous rocks. And then I've circled, to make it a little clear, where there's a bunch of little white dots, all right? And these white dots represent other craters that have been identified, but haven't been adequately studied, or there isn't quite enough evidence for them to firmly say, yes, we think these are part of the same crater cluster. But nonetheless, you can see these cover a large range. And then the other thing they've done is, and I haven't shown you a picture of the craters yet, but some of the craters are elliptical. Now, most every crater on Earth that comes from an asteroid impact, even if the asteroid came in at an oblique angle, by the time it strikes the Earth, all right, by the time it's slowed down by the atmosphere and it falls to Earth and it strikes the Earth, and the immense energy involved, it usually creates a circular crater. In this case, the craters here, many of them are elliptical, and because they're elliptical, you can figure out the trajectory which the rock struck, right? That particular spot. And then knowing the direction that it struck from, you can simply infer backwards, right? And you can look back like, well, where did this come from? And you can see that they have these little shadows saying like, oh, from these dots up here, more toward the north, the ellipses then are pointing back to an area that's on the border between Nebraska and Wyoming. And the ones that are more over here on the west side, right, where it says FRX and PCR, all right, those ellipses are actually pointing in the same direction. All right, so that's pretty interesting evidence, right? Powerful evidence that all these objects, all these craters were created by pieces of large chunks of rock that were thrown up from the Earth from a larger impact and thrown 100 miles away, right, in some cases, and then landed back on the Earth, creating these secondary craters. Those secondary craters probably created in some, they think they were in some kind of like either a very shallow lacustrine environment, so wet environment, and sort of like bloop right there, and made these, and then conditions were such that they got covered up by sediments over time, and then everything turned to rock, and so you have these craters that are preserved for us. Now, what about the original crater? Now, that's the thing in this paper saying, well, like we've now identified all these secondary craters, and they point back to the existence of a primary crater, but we don't actually have the evidence for the primary crater yet. Unfortunately, the rock that's that age, 280 million years old, is buried very deeply under this area of southeastern Utah, southeastern Wyoming and Nebraska. And they even hope in the paper, right? That people that drill oil wells and so forth would be willing to share some data and be able to maybe do their own drilling and maybe drill a little bit deeper and take a look to see if there's any of the typical signs of the kind of impact things that happen. So you have shock quartz, you might have iridium, you might have various rare earth elements and so forth that would be evidence there was actually an actual meteorite that's vaporized at that particular location. So they're hoping to someday find evidence for that. They say there is a weak signature, a gravity, we'll call it a gravity anomaly in that particular area that suggests some kind of compression of the earth underneath that. But they think this could have happened also in kind of a shallow sea, in which case there's not going to be many really clear evidence of a crater that's being buried. It's probably that the edges of the crater have been completely smoothed off and worn down before you ever had any preservation of that area. So whether we'll actually have definitive evidence someday that there is this very large impact crater is yet to be determined. But most everyone I've seen that's commented on this thinks that these secondary craters are very powerful evidence of an actual event that took place 280 million years ago at this particular location. How big would it have been? Certainly not nearly the size of something like the Chicxulub crater in the Yucatan Peninsula, which ended up potentially changing the environment of the whole Earth. But they do think that this would have wiped out really pretty much every living thing within a few hundred miles diameter in this particular area, like giant fireball, huge shock waves. I mean, it would have been very dramatic and would have affected all of North America and to some extent the Northern Hemisphere for some period of time, but not a completely global chaotic event. All right, one other last thing to mention. Oh, yeah, I forgot. I should scroll down here and show you a little bit of the rest of the paper. Oh, this figure just shows that many of the craters are kind of similar in size. So it's a lot of similar sized material that's thrown out and is landing that far away. Oh, and if I could just go back to this figure again, there's only a few places where we have this rock, this age, that's expressed and eroded at the surface where we can actually look at it. Now, here are a couple of those craters. Now, I know they don't look like a whole lot. They're not really spectacular. Remember, they're not that big. But you have to remember that the sedimentary layers that these are found in are generally shallow marine or lacustrine layers, sandstones, shales. They don't have a whole lot of other texture necessarily. And so if you see like these large bowl-like structures and hardened material around the edges, you have to ask yourself, where did that come from? Like if you were there at that time, what kind of force would create these particular structures? Doesn't seem like these would be some kind of, they're too large for like to blame it on a particular group of animals making a whole bunch of nests or somehow changing their environment in some way, or this like some kind of termite mound, or like this is too big for that. It feels like it has to be some kind of geological force. So you could say, well, maybe they're the remnants of some kind of like small volcanic activity, but that would be pretty obvious. There would be volcanic type rocks in the particular area. There'd be some kind of dike that comes up that would have brought volcanic material to the surface at this particular point in time, and no such thing exists. This is all found in shales and sandstones and so forth. And so I guess a large concretion might be possible as well, but that would be an absolutely enormous concretion to have occurred and developed over time. And, you can't expect them to look fantastic because they're not young. 280 million years old. They would have undergone some kind of erosion probably after the initial event before they were buried and preserved. And then after they've been exposed, right, because there's a lot of rock on top of them in this particular area of Wyoming has been eroding. And so in these particular areas where this particular rock is finally reaching the surface, we are now seeing these things confronting us. But they're also eroding, and some of them have probably been at the surface for thousands of years, if not tens of thousands of years. So these craters are eroding. And so there really aren't, as we saw in this picture here, there aren't many locations where this particular aged rock is at the surface for us to even inspect. And even where it is at the surface, that sort of aged rock is possibly already eroded away, or at least the particular layer that has the most obvious evidence of being a crater is eroded away. And we'll never know that there were other craters there. But the sheer number of ones they found at different locations where this particular rock is available to them is pretty amazing, which suggests that really it looks like there was probably hundreds of thousands of little tiny craters all around. And some of those are still buried today, and in the future they will be exposed. There may be some ways of using ground penetrating radar and so forth to look at places where we might guess we might find them and find some more. I don't think it'll do that because that costs money, and there's already enough evidence that that's what these are. We don't need to find more to confirm our hypothesis at this point, probably. So there's some craters. Here's some, actually you can see a couple people off in the distance on the side of this crater. So that gives you an idea of the size of these structures. And like you said, you might hike in an area like this and just not even for a second think about, why is this little bowl here? How did that erode? And you might think that's just some kind of natural erosive event that might just occur from rainfall on rock. And you don't think about the fact that, well, why did it form in this particular structure? It's because there is a hardened layer of rock, the brim of this crater, which is creating this different structure as opposed to basically everything else being flat and eroding in very predictable patterns. Just another example of that we're still finding evidence of large meteor impacts that have struck the Earth, and this all goes into a large database that then helps us to understand what is the frequency at which the Earth gets impacted by these types of objects. Yeah, I mentioned that I spent some time. I think we spent almost a full 7 days in the Bighorn Basin. We actually rented a house. It was an old school house. Literally felt like in the middle of nowhere. There was nothing next to it. And we just had desert around us. And so we went from there exploring a bunch of different directions, the Bighorn Mountains, and we could go through all the desert areas, the Bighorn Basin. And we were there to look for dinosaur bones and anything else we could find. And so one day I took very early in the day, because it gets very hot there in the summer. We left very early, and two of my sons and I decided we were going to hike this place called Sheep Mountain. I was initially reminded of this today because I read this article and it talked about Sheep Mountain and some of these craters being found there. And I thought, wow, that's really fascinating. I remember seeing something really unusual at this particular location. Then after I looked a little bit more at that figure in the paper I just showed you, I realized that doesn't actually extend all the way up to Sheep Mountain. Sheep Mountain, the Sheep Mountain that I was thinking of, right, is all the way up between the Bighorn Basin and Yellowstone. All right, about halfway in between. And the one Sheep Mountain they're talking about in that particular paper was down, I guess, east of Casper, which is a good 150 to 200 miles south of where we were. So this particular debris field probably didn't reach as far as the place where we were hiking. But my initial thought was, wow, I wonder if what I saw in those hills that day, the thing that I wondered about, and actually sat there and thought for a couple minutes, like, what in the heck happened here? Way back in the past when these rocks were formed. really caught my interest. So I had to go back and look up my pictures and see if I had actually taken a picture of the thing that I was thinking about. Now I realize that it's probably most likely not connected to this event. I don't know. If you could throw a bus-sized rocks, 100 miles in the air, I guess you could throw smaller objects even farther away. So potentially there was a rain of rocks in this particular area. And we were walking through some rock that was quite old. All right, we're walking through rock up into the Triassic and eventually into the Jurassic. And so here we are. So on the left-hand side is the beginnings, the foothills of Sheep Mountain, which isn't going to really look like a mountain to you. It's actually a long ridge, and it's an anticline, so it's basically a big bulge. And so all these layered rocks that at one time were horizontal are basically been pushed up and bent over in this big hump. And then they've been eroded over time. And so the great thing about climbing up, and one of the reasons I wanted to climb up this side of this thing, was that as you climb up through it, you keep climbing through more different layers of rock. That's one of my sons walking up the side of this shale that's everywhere, just to give you a sense of scale. All right, so here's a whole layer of this shale. And then we're climbing up over that, and we get to another ridge. You have to kind of go down, climb up to the next ridge, go down, climb up the next ridge. So it's one after another. There he is, way off in the distance, and I'm falling way behind. But here's what I want to show you, and this is very undramatic. But I was walking up one of the sides of one of these hills where everything pretty much is very smooth and even. Like the erosion follows a very regular pattern, and the rock all has the same kind of texture. It's basically very brittle stuff, and it's sort of like it's eroding and falling apart. So all of a sudden, I reach this point where there's this area about I'm going to say about 20 feet wide, 20 by 20. And this area was all of a sudden had this gnarly rock that was much harder. All right, much harder. Let me say, I've got one more picture here. And again, these pictures don't do it justice. I wasn't really thinking about it at the time. I just kind of took a couple shots and thought I'd come back and look at those and see if there's anything interesting later. But this whole region right here in the front, toward the front here, is this much harder rock, and I just don't have a good image of the fact that there was these patterns in this rock. And I remember thinking, is this just because of course we're in Wyoming and there's a lot of dinosaurs in the Bighorn Basin. And I'm thinking I am not in the right kind of rock, because I looked at my geological map and I knew it wasn't really in the right zone for dinosaurs. In fact, I was probably too old and the wrong kind of environment as too. And because it's mostly shallow sea stuff. And I'm looking at this, I'm thinking, this is like a really huge thing and has some really interesting texture to it. I don't know how how does this form in a shallow sea? What happened here? Was this a group of organisms that churned up the soil and so made it different somehow? All right. So as near as I could figure there, I figured this is some kind of concretion. This is some kind of crystalline thing that's happening here that's a secondary effect that happened long after the layers were laid down. It's all part of other layers being heaped on, and then crystal form, giant concretion forms in there. I always forget how to describe how concretions form in rock. But this thing is really big. And so it was like, that just really hit me when I read about these secondary impacts, because I thought, all of a sudden it hit me like, oh yeah, you know what? I saw something that looks like it could have been if a large chunk of rock were to somehow land really, really, huge piece of rock that also has different minerals in it, like brings in a whole bunch more silica or something like that, a bunch of quartz crystals, and just sort of deposit them right there. The impact itself, plus bringing in different materials, and then just that ends up right there, and then it all gets covered up. That could result in a very different lithology of this particular rock at this particular place. And there was sort of a center to it too, and you can't see it here, but to me it felt like you could peel away the layers around it. And then out toward the edge, it suddenly went back to just like very typical brittle, small little pieces of material. That's, by the way, there are lots and lots and lots of fossils at this location, but not everywhere. I have another video that talks about the extreme differences in terms of like one layer having billions of fossils and the next layer having no fossils at all, and sort of the importance for understanding the process of building the fossil record. And there we are near the top of one of the ridges, one of the large ridges, and now we're looking out over, I think that's Triassic sandstones right there, the red stuff. More Triassic sandstones, and that's actually some of the area that's more prone to have your dinosaur fossils in. There I am. And now we got to go back, and believe it or not, my car is somewhere out there, way off in the distance. And there it is. Sorry, the color's pretty washed out because at this point it's about noon, so a lot of direct heavy light and not having the right filter on my camera at the time. Yeah, as somebody who likes to do a lot of photography, I'm almost embarrassed to show these pictures, but yeah, they are what they are. I just throw in a pretty simple story for today. I don't want to make this too long, so pretty simple story for today. Don't want to make this too long, but I want to throw in one extra little caveat to this. And that is, when I talk about something like young earth creationism, and young earth creationists who think that like all these different layers of rock that I've walked through as we've gone through up Sheep Mountain, all those different layers of rock represent layers of sediment that were laid down all at one time in 1 year during Noah's global flood. And it's when you actually go to a place like this and you spend some time and you walk those hills and you walk from one layer to another and you see different fossils. You see the colors change as you see the different mineral contents change in different layers, and you see how stark the contrast is between some of those different layers. That particular scenario of this all being laid down all pretty much at one time makes no sense. But then when you toss in something like the whole area of Wyoming, and you think about this large area of Wyoming, and these secondary craters have been found, all right? And it's not like you find these in all these other layers. It's just in one particular layer that these secondary craters are found with these particular characteristics. And I didn't show you the shock quartz and some of the other like types of measurements they actually made at these craters that show that they're like each other, all right? They have similar properties. But imagine you're in a global flood and you're trying to explain, how did you get these little craters just in this one little layer of rock that's dated to a particular age? Across a very large area, hundreds of square miles, and here you have these little pock marks, right? During a global deluge, when presumably the entire world is covered with water, and it's sloshing around and it's very, very quickly adding sediments to each other. How do you get a whole bunch of little pieces, even if there was a meteorite, right? Even if there was a meteorite during that time that rained down on the earth and punched little holes, how would it punch holes in exactly the same age of rock in different locations, as if all that same exact sediment is being laid down in the same spots at the same time? Just, when it's going to have to lay down thousands of feet of sediment over a period of just a few months. And how do you do that underneath water, right? This really makes perfect sense if you're thinking, oh, well, at some point, 280 million years ago, there is a particular environment in the area that is now Wyoming. There are maybe a shallow sea over here, and there's some slight upland area over here, and you have some wetlands and so forth, and boom, this meteorite comes down, strikes the earth, throws up lots of material. It sprays out over hundreds of square miles, lands in different surfaces in different areas. And every one of those particular areas is that particular age at that moment in time. The surface is that age, right? And then some of those areas get covered up with sediments, and those particular craters get preserved. And they're preserved under 1,000 feet or more, some places 2,000 feet of layers of rock from the Triassic and Jurassic and Cretaceous, then maybe rocks from the Eocene. And then Many of these areas have been uplifted and now they're eroding. And as they erode, they begin to show off their past ages, right? And some areas have eroded down into that Carboniferous rock that's 280 million years old. And when it does so, it shows us that history. It shows us that point in time when that particular event took place. And what's amazing is we can reconstruct that event in a very reasonable fashion because we're using, in this case, I really love this example because it's sort of like, okay, craters, there's only so many explanations you can get for a round or elliptical pattern in the rock, right? How are you going to explain that kind of pattern, especially at that particular size? It's got to be the result of an impact. And then to have the impacts be elliptical and then be able to point all those ellipses toward another location that suggests an original meteorite, and to have the additional evidence that these secondary craters are secondary craters because they are missing some things that they would have if they were primary craters directly from meteorites. Right, so all the evidence adds up together. It all points to, right, there's a consilience of that data. It points to a particular answer or a particular hypothesis, which now has some pretty good support for it. It's as if we have a window into that moment in time when that happened. Just like that crater on the Yucatan Peninsula, there's so much supporting evidence for that. It's hard to deny there wasn't that dramatic event that occurred. And young Earth creationists, most of them acknowledge that must have been a meteorite impact. And so they have to try to somehow accommodate that in the middle of a flood, which is incredibly difficult. So difficult that some creationists actually deny that was even a crater as well, created by an extraterrestrial impact. I think something like this crater is, in a way, maybe even harder to explain within the global flood context. Anyway, that's all I wanted to do today. It brought back memories of my our trip to Wyoming and our time in the desert there, which is always great because lots of rocks to look at, lots of fossils, lots of interesting animals too. Forgot to put a picture of pronghorn in there because I took a lot of pronghorn pictures when I was in Wyoming. Fantastic animals. All right, that's it for me today. Thank you very much for listening. We'll talk to you later. Bye-bye.